Out in the vast ocean of space, something strange is happening, something invisible, something enormous, and something we still don't fully understand. Galaxies, those glittering islands of stars, aren't moving the way they should. They spin too fast, cluster too tightly, and dance in ways that defy the laws of gravity as we know them. What's pulling the strings behind this cosmic performance? The answer lies hidden in the shadows of the universe itself, dark matter. This mysterious substance, invisible to our telescopes yet holding galaxies together like an unseen hand, is just the beginning of a far grander enigma, the cosmic dark matter web. Picture it as an immense, invisible skeleton stretching across the universe, a network of filaments connecting galaxies in a vast, dark architecture. And woven into this web are at least 25 mysteries that challenge everything we think we know about the cosmos. Imagine standing at the edge of discovery, peering into the abyss of the unknown. This isn't just about invisible matter, it's about the hidden scaffolding of reality itself. Why do galaxies align along these dark threads like pearls on a string? How does this phantom web shape the birth and death of stars? And what lurks in the voids between, where dark matter seems to whisper secrets we can't yet decipher? Every clue we uncover only leads to deeper questions, pulling us further into a puzzle that spans billions of light years. This journey isn't just for scientists, it's for anyone who's ever looked up at the night sky and wondered what's really out there. Because the cosmic dark matter web isn't some distant abstraction, it's the hidden framework of everything we see, the silent architect of the universe. And as we unravel its 25 greatest mysteries, we're not just exploring space, we're rewriting the story of existence itself. So take a step into the unknown with us. The universe has been keeping secrets, and it's time we uncover them together. At the heart of our cosmic mystery lies a structure so vast and invisible, it defies ordinary perception, the dark matter web. Think of it as the universe's hidden blueprint, an intricate network of filaments stretching across billions of light years, weaving galaxies together like beads on an invisible string. Without it, the night sky as we know it wouldn't exist. Galaxies would fly apart, stars would scatter, and the universe would lose its grand architecture. But how do we study something we can't see? That's where nature itself steps in as our guide. When light from distant galaxies travels through space, it doesn't always follow a straight path. Instead, it bends around massive clumps of dark matter, warping like a funhouse mirror. This phenomenon, called gravitational lensing, lets astronomers map the unseen. By studying these distortions, we've uncovered ghostly filaments connecting galaxy clusters, revealing a web far more complex than anyone imagined. Supercomputer simulations show dark matter swirling into delicate threads, knotting at intersections where galaxies gather. Yet here's the puzzle. If we can trace its shape, why can't we pinpoint what it's made of? Some theories suggest particles unlike any we've detected, lurking just beyond our experiments. Others propose hidden dimensions bending the rules of physics. Every time we think we're close, dark matter slips through our grasp, leaving behind more questions than answers. But one thing's certain, this invisible skeleton doesn't just hold the universe together. It shapes how galaxies form, where stars ignite, and perhaps even how time itself unfolds. And until we crack its code, the cosmos will keep its greatest secret hidden in plain sight. If dark matter is truly everywhere, weaving through your hands as you listen and filling the spaces between galaxies, why haven't we caught a single particle of it? This isn't just a scientific hiccup, it's a full-blown cosmic whodunit. For decades, physicists have been hunting for a suspect called WIMP, or weakly interacting massive particles. These elusive entities should be everywhere, barely touching ordinary matter except through gravity. Underground labs shielded from cosmic rays, miles of detectors chilled to near absolute zero, all lying in wait for the faintest whisper of a collision. Yet after years of listening, the silence is deafening. WIMP aren't the only suspects, though. Actions, hypothetical particles lighter than a feather's breadth, could be streaming through us right now. Then there's sterile neutrinos, ghostly cousins to the ones we've detected, or even primordial black holes forged in the universe's first second. Each theory is a door to a stranger reality, but every time we turn the handle, the room beyond stays dark. The problem isn't just finding dark matter. It's that the universe refuses to follow our playbook. Maybe we're searching for the wrong things, or perhaps dark matter isn't matter at all but a shadow of deeper physics, a flaw in Einstein's equations or a hidden force bending space itself. Every dead end forces us to rethink the rules, and that's the real mystery here. Not just what dark matter is, but what its elusiveness teaches us about the limits of human ingenuity. The cosmos loves a good puzzle, and this one's far from solved. Deep in the cosmos, where the rules of galaxy formation should be clear-cut, astronomers keep stumbling upon cosmic rebels galaxies that simply shouldn't exist. Take Dragonfly 44, a shadowy giant lurking in the Coma cluster. It's as massive as our Milky Way, but with a fraction of its stars. This isn't just a dim galaxy. It's a ghostly leviathan where dark matter outweighs visible matter by a staggering ratio of 10,000 to 1. How does a galaxy this massive end up almost empty, like a mansion with just a single light bulb flickering inside? The puzzle deepens when we realize Dragonfly 44 isn't alone. Across the universe, astronomers are spotting more of these ultra-diffuse galaxies, faint, wispy structures that defy every model of how galaxies form. Conventional wisdom says galaxies grow by swallowing gas, igniting stars, and becoming brighter over time, but these cosmic oddballs flip the script. Their dark matter halos are colossal, yet star formation barely happened. It's as if the universe forgot to turn on the lights. One theory suggests these galaxies are failed Milky Ways, places where dark matter clumped together as usual, but star-forming gas got stripped away by violent encounters with other galaxies. Another idea points to extreme environments like galaxy clusters, where tidal forces might have stretched them thin, leaving behind dark matter skeletons with only a sprinkle of stars. But neither explanation fully fits. If tidal forces sculpted them, why do some exist in isolation? And if they're failed galaxies, why do their dark matter halos appear too perfectly intact? The most unsettling possibility, our understanding of dark matter itself might be incomplete. Maybe dark matter interacts in ways we haven't predicted, creating pockets where galaxies form stars reluctantly or not at all. Every time we think we've cracked the case, these cosmic enigmas whisper, "Think again." They're not just curiosities, they're stress tests for our theories, revealing gaps in our knowledge as wide as the voids between galaxies. And until we solve them, the universe's blueprint remains half-written, its secrets hidden in the darkness. Even our own cosmic backyard, the Milky Way, holds dark matter secrets that refuse to line up neatly. Scientists have spent decades trying to weigh our galaxy's invisible halo, the vast, ghostly cocoon of dark matter that surrounds us, but the numbers keep clashing. One method, tracking how fast stars orbit the galaxy's outskirts, suggests a lighter halo, while another, studying how the Milky Way tugs on smaller satellite galaxies, points to something far heavier. It's like stepping on two scales and getting wildly different readings, leaving astronomers scratching their heads over which one to trust. The plot thickens when we zoom in on the halo's shape. Some models predict dark matter should pile up densely at the galaxy's core, forming a sharp cusp, while others argue it's more evenly spread, leaving a core of relatively constant density. Observations don't settle the debate, they fuel it. Dwarf galaxies orbiting the Milky Way seem to favor cores, while simulations of galaxy formation overwhelmingly lean toward cusps. This isn't just academic nitpicking. If dark matter clusters differently than we expect, it could mean our simulations are missing a key piece of physics, or that dark matter interacts with itself in ways we haven't accounted for. Take the puzzling case of our galactic neighbor, the Large Magellanic Cloud. Its gravity appears to be warping the Milky Way's dark matter halo, dragging part of it along like an invisible wake. If dark matter were truly frictionless and non-interacting, as most models assume, this shouldn't happen so dramatically. Yet here we are, watching our own galaxy's hidden structure twist in ways that defy textbook predictions. These contradictions aren't just measurement errors, they're clues. Maybe dark matter isn't the simple, inert stuff we've imagined. Perhaps it subtly interacts with itself or with ordinary matter through some unknown force. Or maybe the Milky Way's violent history collisions with smaller galaxies, bursts of star formation, has stirred the dark matter pot, leaving a messier distribution than pristine simulations anticipate. Every discrepancy forces us to reconsider the rules, turning our home galaxy into a cosmic laboratory where the deepest mysteries of the universe are playing out right over our heads. But perhaps the most unsettling question of all isn't just what dark matter is, but what it might be doing to the universe itself. For decades, we've assumed dark matter was a passive player in cosmic expansion, its gravity gently pulling galaxies together while dark energy pushes them apart. But what if these two invisible forces aren't just coexisting? What if they're locked in a hidden dialogue, shaping the fate of the cosmos in ways we never anticipated? The numbers tell a strange story. When astronomers first discovered the universe's expansion was accelerating, they pinned it on dark energy, an enigmatic force ripping space apart. But here's the hitch: the rate of that acceleration doesn't quite match our predictions. Dark matter's gravitational grip should be slowing expansion more than we observe, as if something's subtly counteracting its pull. Could dark matter itself be decaying, transforming into something else over billions of years? Or worse, could it be interacting with dark energy, fueling the expansion like a cosmic feedback loop? Some theorists propose a radical idea. Dark matter and dark energy might not be separate entities at all. Instead, they could be different faces of the same shadowy phenomenon, a single substance that behaves like matter in some contexts and like repulsive energy in others. Imagine a chameleon field, shifting its properties based on the density of its surroundings, clumping like matter in galaxy clusters, but pushing space apart in the voids between. If true, this would rewrite the rules of cosmology, blending two mysteries into one. Yet the evidence remains frustratingly indirect. In dense regions like galaxy clusters, dark matter's gravity dominates, but in the vast cosmic deserts between filaments, dark energy takes over. The transition between these regimes could hold the key. If dark matter's influence wanes as the universe expands, or if it leaks energy into the vacuum of space, it might explain why expansion is winning the tug of war. But proving it, that's another challenge entirely. For now, every telescope and simulation brings us closer to the edge of understanding, or the brink of a paradigm shift. The universe isn't just expanding, it's doing so on terms we don't fully grasp. And if dark matter is secretly conspiring with dark energy, then the cosmos is playing a far more intricate game than we ever imagined. One thing's certain: the deeper we look, the stranger the rules become. Somewhere beyond the edge of our observable universe, something immense is pulling. Not just a galaxy or two, but entire clusters of them. Thousands of galaxies hurtling in the same direction at speeds that defy explanation. Astronomers call it the dark flow, and it's one of the most puzzling cosmic mysteries ever recorded. Imagine throwing a handful of dust into the wind, only to watch every speck rush toward a single point on the horizon, as if dragged by an invisible current. That's precisely what's happening on a scale spanning billions of light years. The story began with meticulous observations of galaxy clusters, each one a metropolis of stars, hot gas, and dark matter. By studying the subtle temperature shifts in the cosmic microwave background, the afterglow of the Big Bang, researchers detected something bizarre. these clusters weren't moving randomly. Instead, they streamed together at breakneck speeds toward a region of space with no known supercluster, no colossal black hole, no visible structure massive enough to explain the motion. It's as if the universe has a hidden compass and every needle points toward a place we can't see. The dark flow throws a wrench into our understanding of cosmology. According to the Standard Model, the universe should expand uniformly after the Big Bang, with matter distributed evenly enough that no single direction dominates. Gravity from nearby structures might tug galaxies slightly, but nothing should cause such coordinated motion across such vast distances. Yet here we are, faced with evidence that some enormous gravitational influence far beyond our observational horizon is bending the rules. Theorists have scrambled for explanations. Could it be the gravitational pull of a supermassive structure lurking in the unobservable universe, a cosmic giant so vast it warps space-time across unimaginable distances? Or perhaps the remnants of a pre-Big Bang era, a relic from a parent universe whose gravity still echoes into ours. Some even speculate it's evidence of other bubble universes in the multiverse, their gravity subtly leaking into our own. But here's the catch: the dark flow's very existence is hotly debated. Skeptics argue it might be a statistical fluke or an artifact of measurement errors. Yet multiple independent studies keep detecting the same eerie motion, leaving scientists at a crossroads. If the flow is real, it means our universe isn't just stranger than we imagined, it's stranger than we can imagine. There's an unseen architecture out there, a shadowy hand guiding the motion of galaxies on scales we've barely begun to fathom. And until we peer beyond the cosmic veil, the dark flow remains a haunting reminder of how much we still don't know. If there's one cosmic collision that shook our understanding of dark matter to its core, it's the Bullet Cluster. This violent encounter between two galaxy clusters, located nearly 4 billion light-years away, isn't just a spectacle of destruction, it's a forensic snapshot of the invisible. Here's why it's so groundbreaking. When these clusters collided, their stars barely noticed, passing through each other like ghosts. The hot gas, though, piled up in the middle like two trucks slamming together. But the real shock came when astronomers mapped the mass distribution using gravitational lensing. The bulk of the mass of the dark matter had sailed right through the crash site, leaving the gas behind. It was the first direct proof that dark matter isn't just theoretical, it's real, and it behaves unlike anything made of atoms. But the Bullet Cluster didn't just confirm dark matter's existence, it deepened the mystery. According to simulations, the separation between dark matter and gas should have been cleaner. Instead, some dark matter seems to lag behind, as if it's not entirely immune to the chaos of the collision. Could dark matter interact with itself in ways we never predicted? Some researchers think so. They propose a dark force that allows these particles to nudge each other ever so slightly, creating a faint drag effect. Others argue the anomaly might come from ordinary physics, turbulence in the gas or unseen substructure, but the data keeps pointing to something stranger. Then there's the speed problem. The Bullet Cluster's collision is one of the most energetic events ever observed, with shock waves hotter than the core of our Sun. Yet some models suggest it shouldn't be possible for clusters to hit each other that fast in our universe's timeline. The math implies they'd need a running start, as if an unseen hand gave them an extra gravitational shove. Could this be a hint of dark matter's influence on cosmic structures, not just through gravity but through something more subtle? The Bullet Cluster is more than a smoking gun, it's a mirror reflecting how much we still don't know. Every time we think we've pinned down dark matter's rules, this cosmic crash whispers a new question. Why does some dark matter seem to cling faintly to visible matter? What really governs its behavior in extreme environments? And if dark matter isn't as simple as invisible stuff that only feels gravity, what other surprises is it hiding? One thing's clear: this collision didn't just separate matter, It split open a crack in our understanding, and through it we're glimpsing a universe far more complex than we ever dreamed. Dark matter might not be made of particles at all. What if it's something far stranger, a quantum field humming through the cosmos like an invisible orchestra? This isn't science fiction. Some theorists argue dark matter could be a relic of the universe's first moments, a field of energy frozen into the fabric of space itself. Picture the Higgs field, which gives particles mass, but with a twist. Instead of interacting with atoms, this field only warps space-time, tugging galaxies into place without ever making its presence known directly. The idea flips conventional wisdom on its head, suggesting dark matter isn't discrete clumps but a seamless, cosmic undercurrent shaping reality from the shadows. Then there's the wild card, primordial black holes. These aren't the black holes born from collapsing stars. They'd be ancient, forged in the chaos of the Big Bang's first second, when the universe was so dense that pockets of matter could crumple into tiny, invisible knots. Some could be as light as a paperclip or as massive as a planet, littering the cosmos like dark matter landmines. The allure, they'd explain why we've never detected dark matter particles, because they aren't particles. They're black holes so old they've been hiding in plain sight for 13.8 billion years. But controversy looms over both ideas. If dark matter is a quantum field, why doesn't it leave fingerprints in particle colliders or subtle ripples in the cosmic microwave background? And for primordial black holes, the math is unforgiving. Too many lightweight ones would have evaporated by now, thanks to Hawking radiation, while heavier ones would warp spacetime so noticeably we'd have spotted their gravitational lensing effects. Yet intriguingly, some observations dangle tantalizing hints. Unexplained gravitational wave signals, flickering stars with no clear cause, even oddities in the way light bends around galaxies, all could point to these shadowy suspects. The debate rages because these theories aren't just about dark matter's identity. They're about rewriting physics itself. A quantum field dark matter might require new forces or dimensions, while primordial black holes could mean the Big Bang was far more violent and uneven than we thought. Every failed detection of traditional dark matter particles pushes these fringe ideas closer to the mainstream, forcing scientists to ask, have we been searching for the wrong thing all along? The universe loves a good paradox, and dark matter's quantum weirdness might be its greatest trick yet, hiding not in particles or forces, but in the gaps between our understanding. The Milky Way should be swarming with tiny, faint companions, hundreds, if not thousands, of dwarf galaxies orbiting like fireflies around a street lamp. That's what supercomputer simulations have told us for decades. Yet when astronomers peer into the skies, they count barely a few dozen of these cosmic minnows. This glaring mismatch, known as the missing satellites problem, isn't just a counting error. It's a fundamental crack in our understanding of how galaxies form. Picture this: dark matter halos, those invisible cocoons surrounding galaxies, should be littered with smaller clumps, remnants of the universe's chaotic early days. These clumps act as gravitational seeds, pulling in gas and igniting stars to become dwarf galaxies. Simulations like the famed Millennium Run show a Milky Way drowning in satellites, a bustling crowd of them. Reality, though, paints a lonelier scene. Where are they all hiding? One possibility is that most dwarfs are simply too dim to see. Star formation in these tiny galaxies could have been stifled, perhaps by the searing ultraviolet light from the first stars, which might have boiled away their gas before they could shine brightly. Or maybe the Milky Way's gravity ripped them apart long ago, leaving behind only scattered streams of stars as faint clues. Some of these ghost galaxies might still lurk in our backyard, detectable only through their subtle gravitational tugs or the rare, ancient stars they've left behind. But there's a catch. Even if some dwarfs are cloaked in darkness, their dark matter halos should still be there, bending light and distorting space-time in ways we can measure. Yet when astronomers scan the skies with gravitational lensing surveys, the numbers still don't add up. This suggests something deeper is at play. Maybe dark matter isn't as cold as we've assumed. In the standard model, dark matter is cold, meaning its particles move sluggishly, clumping easily to form structures. But if dark matter were slightly warm, with particles zipping around faster, they'd smooth out those small-scale clumps, preventing dwarf galaxies from forming in the first place. Warm dark matter would solve the missing satellites problem, but it'd also create new headaches, like explaining why we see any dwarf galaxies at all. The plot thickens with the discovery of ultra-faint dwarfs, galaxies so dim they're practically invisible except to our most sensitive telescopes. These ghosts, like Segway 1 or Boötes 1, are barely more than a handful of stars held together by dark matter. Their existence hints that the Milky Way's satellite population might be larger than we thought, just extraordinarily shy. But even adding these faint specks to the ledger leaves us far short of the thousands predicted. So what's the answer? Maybe our simulations are oversimplifying the messy physics of galaxy formation. Or perhaps the universe conspired to erase most dwarfs through cosmic violence we don't yet understand. Alternatively, dark matter could be more complex than a single, sluggish particle, maybe a mix of cold and warm components, or even interacting particles that scatter like billiard balls, disrupting small-scale structure. Every missing satellite is a silent challenge to our models, a whisper from the cosmos that the story we've written about dark matter and galaxy formation is still missing crucial chapters. Until we solve this puzzle, the dwarf galaxy discrepancy will loom over astronomy, a reminder that even in our own galactic neighborhood, the universe keeps its deepest secrets close. One of the most heated debates in modern cosmology doesn't revolve around distant galaxies or shadowy particles. It centers on a single number. The Hubble constant, which measures how fast the universe is expanding, has become a battleground for conflicting measurements. On one side, observations of nearby stars and supernovas suggest a relatively rapid expansion rate. On the other, the cosmic microwave background, the afterglow of the Big Bang, points to a slower, more sedate pace. This discrepancy, known as the Hubble tension, isn't just a rounding error. It's a gaping hole in our cosmic ledger, one that might trace back to dark matter's invisible hand. At first glance, the tension seems unrelated to dark matter. After all, the Hubble constant reflects the present-day expansion rate, while dark matter's gravitational pull mainly influences how structures like galaxies and clusters form. But dig deeper, and the connection becomes unnervingly clear. Our models of the universe rely on a precise recipe, a dash of ordinary matter, a heaping portion of dark matter, and a pinch of dark energy, all mixed together in the aftermath of the Big Bang. If dark matter isn't distributed the way we think, if it clumps differently or interacts in unexpected ways, it could throw off our entire cosmic accounting system. Take the cosmic microwave background, for instance. The Planck satellite's meticulous measurements of this ancient light assume dark matter behaves like a simple, cold, collisionless fluid. But what if it's not? If dark matter particles interact with each other or with dark energy, even weakly, it could alter how quickly structures formed in the early universe. This, in turn, would change the inferred expansion rate, potentially bridging the gap between the conflicting values. Then there's the local universe's peculiarities. When astronomers use supernova as cosmic yardsticks, they're measuring expansion in a region dominated by the gravitational tug of dark matter halos. If those halos are denser, lumpier, or more dynamic than simulations predict, it could skew the apparent rate of expansion. Some theorists speculate that we might live in an underdense bubble, a cosmic valley where dark matter's grip is slightly weaker, making nearby expansion seem faster than it truly is on average. The stakes couldn't be higher. If the Hubble tension stems from a misunderstanding of dark matter, it implies our entire cosmological framework, the so-called lambda cold dark matter model, is missing a crucial ingredient. Perhaps dark matter decays over time, subtly altering gravity's pull. Maybe it's not entirely cold, but lukewarm, with particles just energetic enough to smooth out small-scale structures and tweak the expansion history. Or, most revolutionary of all, dark matter and dark energy might be entangled in a cosmic dance, their interplay shaping the universe's fate in ways no equation yet captures. For now, the tension remains unresolved, a stubborn discrepancy that refuses to vanish under scrutiny. But therein lies the beauty of the mystery. Like a detective scrutinizing a suspect's alibi, scientists are poring over every detail, testing alternative dark matter theories against a mountain of data. Each new observation, whether of gravitational lenses, galaxy clusters, or the ripples of spacetime itself, brings us closer to knowing whether dark matter is the silent culprit behind cosmology's greatest rift. And when the answer finally comes, it won't just settle a debate about numbers. It'll rewrite the story of how our universe grows, evolves, and ultimately unravels. At the heart of the dark matter mystery lies a fundamental question. Is it slow, lumbering, and icy, or quick, zippy, and warm? This isn't just semantics. The difference between cold and warm dark matter could reshape everything we know about galaxy formation, cosmic structure, and even the fate of the universe. For decades, the leading theory has been cold dark matter, particles that move sluggishly, barely above a cosmic standstill. Picture syrup pouring in slow motion, clumping into thick pools where gravity pulls hardest. This model excels at explaining the universe's largest structures, galaxy clusters, sprawling filaments, and vast voids, but zoom in and cracks appear. Cold dark matter predicts countless dwarf galaxies swarming around giants like the Milky Way, yet we observe far fewer than expected. It also struggles with galaxies like Dragonfly 44, where dark matter outweighs stars 10,000 to 1. How could such extreme imbalances arise if dark matter clumps so efficiently? Enter warm dark matter, the underdog theory where particles zip around faster, like moths flitting through a spotlight. These particles wouldn't clump as easily on small scales, smoothing out the excess dwarf galaxies and potentially explaining why some galaxies stay eerily dim. But here's the catch: warm dark matter might smooth things too much. It struggles to account for the very earliest galaxies, which appear to have formed surprisingly quickly after the Big Bang. Without enough dense clumps to seed them, how did these ancient galaxies ignite so soon? The debate isn't just academic, it's playing out in real cosmic oddities. Take ultra-diffuse galaxies, those ghostly realms where stars are few and far between. Cold dark matter expects them to be rare, while warm dark matter predicts them in droves. Yet some, like NGC 1052DF2, defy both models by existing in isolation, far from the disruptive pull of larger galaxies. Then there's the cosmic web itself. Cold dark matter simulations produce intricate filaments that match observations stunningly well, until you notice subtle discrepancies in how galaxies align along them. Warm dark matter tweaks these patterns, but neither nails it perfectly. The solution might lie somewhere in the middle. Perhaps dark matter isn't purely cold or warm, but a mix, like two types of sand, one coarse, one fine, filling the cosmic hourglass together. Or maybe dark matter's behavior changes over time, starting warm in the early universe and cooling as expansion slows its particles. Some theorists even propose fuzzy dark matter, where particles are so lightweight they behave like quantum waves, blurring the line between particle and field. Every observation adds a new twist. Gravitational lensing studies, which map dark matter's distribution, reveal halos that are sometimes smoother, hinting at warmth, and sometimes clumpier, favoring cold. The universe seems to be taunting us, offering clues that point in both directions at once. Until we catch dark matter in the act, whether in a lab or through some ingenious astronomical proxy, this debate will rage on. And that's the beauty of it. The answer won't just tell us what dark matter is. It'll rewrite the story of how our universe builds its grandest structures, one invisible particle at a time. Vera Rubin stared at the data, and the data stared back defiant. It was the 1970s, and astronomers assumed galaxies behaved predictably, their outer stars orbiting more slowly than the inner ones, just like planets in our solar system. But Rubin's meticulous observations of the Andromeda Galaxy revealed something bizarre. No matter how far a star was from the center, it zipped along at nearly the same speed. This wasn't just unexpected, it violated the laws of gravity as we knew them. If visible matter alone held galaxies together, those outer stars should have been flung into the void. Yet there they were, clinging to the edges at speeds that made no sense unless something invisible was holding them in place. That something was dark matter, and Rubin's work became the smoking gun for its existence. Her discovery hinged on rotation curves graphs plotting star speeds against their distance from a galaxy's core. In a universe governed only by visible mass, these curves should slope sharply downward like a roller coaster dropping after a steep climb. Instead, Rubin found curves flat as a tabletop, a cosmic sleight of hand demanding an unseen hand. The conclusion was inescapable. Galaxies were cocooned in vast halos of dark matter, their gravity propping up stellar speeds where ordinary matter's grip should have faded. Yet even this landmark revelation left puzzles unsolved. Take ultra-diffuse galaxies like NGC 1052DF2, where stars are so sparse you could fly through one and barely see a twinkle. These ghostly realms should be dominated by dark matter's grip, yet some rotate as if the phantom halo is barely there. Then there's the opposite extreme, galaxies like Dragonfly 44, where rotation curves suggest dark matter is so overwhelming, it's as if the stars are an afterthought. Why do some galaxies follow Rubin's rulebook while others tear it up? One theory points to feedback, violent bursts of star formation, or supermassive black holes blasting gas outward, disrupting the dark matter's distribution. Another suggests dark matter isn't uniform but comes in flavors, with some types interacting in ways that smooth out halos or clump them unpredictably. And then there's the radical idea that we're seeing not dark matter's quirks, but gravity itself misbehaving at galactic scales, a possibility that sends theorists back to the drawing board. Rubin's rotation curves cracked open the door to dark matter, but the view beyond is weirder than anyone imagined. For every galaxy that fits the mold, another rebels, spinning too fast or too slow, as if the universe is teasing us with half-truths. These outliers aren't just anomalies, they're stress tests for our theories, proving that even after 50 years, the phantom of galaxy rotation still has secrets to spill. And until we solve them, the true nature of dark matter will keep slipping through our fingers, as elusive as the stars it holds in orbit. In 2014, a faint but persistent whisper from the cosmos sent shockwaves through the astrophysics community. The European Space Agency's XMM Newton telescope had picked up an odd spike in X-ray emissions. A tiny bump at 3.5 kilo-electron volts, lingering in the spectra of distant galaxy clusters. At first glance, it seemed unremarkable, just another blip in the universe's chaotic electromagnetic static. But when researchers noticed the same signal cropping up repeatedly, from the Perseus cluster to the Andromeda Galaxy, excitement turned to outright speculation. Could this be the long-awaited fingerprint of dark matter itself? A telltale sign of particles decaying into photons after billions of years in hiding. The implications were staggering. If dark matter decays even imperceptibly, it would mean this shadowy substance isn't entirely inert. Instead of merely lurking in halos, tugging on galaxies with gravity alone, it might slowly unravel, shedding energy like a cosmic hourglass trickling sand. The 3.5 keV line fit tantalizingly well with predictions for sterile neutrinos, hypothetical particles that could bridge the gap between ordinary matter and the unseen bulk of the universe. Here, at last, was a signal that didn't require elaborate underground detectors or particle colliders. The universe itself might be broadcasting dark matter's secrets in X-rays. But science thrives on skepticism, and the 3.5 keV line soon became one of the most hotly debated anomalies in modern astronomy. Critics argued the signal could be an artifact of instrumental noise or an overlooked atomic transition in hot plasma. Sulfur ions, common in galaxy clusters, emit X-rays at nearly the same energy, a coincidence that muddied the waters. Then came conflicting observations. NASA Chandra X-ray Observatory failed to detect the line in some regions where it should have shone brightly, while Japan's Hitomi satellite, before its tragic malfunction, reported no trace of it in the Perseus cluster at all. The signal flickered in and out of focus like a mirage, leaving researchers divided. The controversy only deepened when independent teams began scouring other datasets. Some found the line in unexpected places, like the Milky Way center or even the cosmic X-ray background, the diffuse glow from all X-ray sources across the universe. Others, analyzing the same data with different methods, saw nothing. The debate grew so polarized that papers arguing for and against the signal's existence sometimes appeared back-to-back in the same journals, a scientific stalemate with no clear resolution. What makes this mystery so compelling isn't just the potential discovery, it's the sheer audacity of the claim. Detecting dark matter through its decay would revolutionize particle physics, offering a direct window into the invisible majority of the cosmos. But extraordinary claims demand extraordinary evidence, and the 3.5 keV line remains tantalizingly ambiguous. It's a reminder that the universe often speaks in riddles, scattering clues just clear enough to spark debate but too faint to settle it. Until a future telescope or a bold new theory cuts through the noise, this enigmatic signal will linger at the edge of discovery, a haunting melody in the dark matter symphony we've only begun to hear. What if dark matter isn't just sitting there silently shaping the cosmos? What if it's actively pushing, pulling, and whispering to itself through a hidden language of physics? The idea of a fifth force governing dark matter's behavior started as a fringe theory, but mounting evidence suggests this invisible hand might be tweaking the rules of the universe in ways we never anticipated. Take galaxy cluster Abell 521, where dark matter appears to lag behind the visible stars and gas during collisions, as if something's subtly dragging its feet. If dark matter only felt gravity, this hesitation wouldn't exist, yet there it is, hinting at interactions beyond our standard model. The concept flips everything we assumed about dark matter on its head. Ordinary matter experiences four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Dark matter, we thought, only cared about gravity. But scattered observations paint a different picture. Some dwarf galaxies show dark matter halos suspiciously smoother than simulations predict, as if an unseen pressure evenly distributed their mass. Elsewhere, certain galaxy rotations defy expectations unless dark matter particles nudge each other apart like magnets with reversed polarity. These anomalies suggest a hidden force could be at work, one that only operates in the shadow realm of dark matter. How might such a force behave? Theorists propose wild possibilities. Perhaps dark matter particles carry a dark charge, creating fields that repel or attract their own kind while ignoring ordinary matter entirely. This could explain why some galaxy clusters seem to have dark matter heated up, spreading outward like steam escaping a kettle. Alternatively, the force might be short-range, only kicking in when dark matter particles come extraordinarily close, a cosmic game of tag where the players barely brush past one another. The most radical idea: dark matter could mediate its force through undiscovered particles, a shadow version of photons or gluons that weave an intricate, invisible web of influence across the universe. Critics argue these theories add unnecessary complexity, that Occam's razor should slice away speculative forces in favor of tweaking existing models. But the universe has never been shy about embracing complexity. After all, the discovery of dark energy shattered the illusion that gravity alone dictated cosmic expansion. Why shouldn't dark matter have surprises of its own? The smoking gun might lie in extreme environments, regions where dark matter is so densely packed that any self-interactions would amplify. Observations of colliding galaxy clusters like the famous train wreck cluster Abell 520 could hold the key. If dark matter halos distort in ways that gravity alone can't explain, we might finally catch this fifth force in the act. For now, the mystery lingers like a shadow just beyond our reach. Every unexplained galactic quirk, every odd halo shape, whispers the same tantalizing question: is dark matter playing by rules we haven't even written yet? The answer could rewrite not just dark matter's story, but the entire playbook of fundamental physics. And that's the thrill of the hunt. Each strange observation might be the thread that unravels the universe's best-kept secret. NGC 1052DF2 isn't just another galaxy, it's a cosmic heretic. While the rest of the universe seems shackled by dark matter's invisible grip, this faint, wispy island of stars floats freely, as if the rules don't apply. Discovered in 2018, it sent shockwaves through astronomy for one startling reason. Measurements suggested it contained no dark matter at all. Not just a little less than expected, but none. Imagine finding a skyscraper floating in midair with no steel frame. That's how radically this defies our understanding of how galaxies form. At first glance, NGC 1052DF2 looks unremarkable. It's an ultra-diffuse galaxy, a type known for being ghostly and sparse. But when scientists calculated its mass by observing the motion of its star clusters, something didn't add up. The visible stars alone accounted for nearly all its gravity, leaving no room for dark matter's usual dominance. To confirm, researchers turned to the Hubble Space Telescope, meticulously counting globular clusters, dense groups of ancient stars that typically orbit galaxies like bees around a hive. Their speeds betrayed the galaxy's true weight, and the verdict was undeniable. This galaxy had somehow evaded dark matter's grasp entirely. The discovery sparked instant controversy. Skeptics argued the measurements might be off, perhaps due to the galaxy's edge on orientation or an unseen tidal force from a neighboring galaxy distorting its structure. Others suggested NGC 1052DF2 could be a tidal dwarf, a rare galaxy born from debris ripped away during a violent collision where dark matter might have been left behind like an abandoned shell. But follow-up observations only deepened the mystery. The galaxy's pristine, undisturbed shape showed no signs of a recent cataclysm, and its star clusters moved too sluggishly to support any hidden mass. It was as if this galaxy had formed in a bubble where dark matter never existed. Then came the plot twist. In 2021, another team reanalyzed the data using a different method and claimed the galaxy did have dark matter after all. Their measurements suggested the star clusters were moving faster than initially thought, implying an unseen gravitational anchor. The debate raged, but the original researchers held firm, countering that the new analysis relied on assumptions about the star cluster's orbits that couldn't be proven. The stalemate left the astronomical community divided, with one side declaring NGC 1052DF2 a dark matter desert, and the other insisting it was business as usual. But here's the kicker. Even if NGC 1052DF2 does harbor some dark matter, its halo would still be embarrassingly anemic compared to similar galaxies. And that raises a deeper question: how could a galaxy end up so unbalanced? If dark matter is the cosmic glue that seeds galaxy formation, How did this one assemble itself without it? Some theorists propose it's a victim of galactic theft, its dark matter stripped away by a close encounter with the massive galaxy NGC 1052. Others wonder if dark matter and visible matter can sometimes separate like oil and water, with certain environments favoring stars over shadowy particles. The most tantalizing possibility, NGC 1052DF2 might not be alone. A handful of other galaxies, like NGC 1052DF4 and KKS 200004, now seem to share its dark matter deficit. If these outliers form a pattern, they could point to a hidden channel of galaxy evolution, one where dark matter isn't the sole architect. Or worse, they might hint that our understanding of gravity itself is flawed, reviving the long-dismissed idea that gravity works differently on galactic scales. For now, NGC 1052DF2 remains a cosmic riddle wrapped in a paradox. Whether it's a fluke or a trailblazer, its existence forces us to confront an uncomfortable truth. The universe might have more than one way to build a galaxy. And until we solve its secret, this ghostly rebel will keep challenging the very foundations of cosmology. Stretching between galaxies like vast, invisible bridges, the filaments of the cosmic web should be bustling highways of dark matter and gas, yet when astronomers train their telescopes on these regions, some appear hauntingly empty. These ghostly threads, predicted by simulations to be dense with matter, instead show up as cosmic mirages, their expected contents mysteriously absent. It's as if the universe built an intricate network of roads but forgot to populate them with traffic. Take the filament connecting the galaxy clusters Able 222 and Able 223, a structure spanning nearly 20 million light-years. Simulations suggested this corridor should be thick with warm gas, a glowing ribbon detectable in X-rays. Yet when the Chandra Observatory examined it, the signal was feeble at best, like turning on a flashlight in a cavern and finding no walls to reflect the beam. Similar gaps appear elsewhere, with some filaments registering only a whisper of the matter they ought to hold. The question isn't just where the missing material went, but why these voids exist in a web supposedly woven by dark matter's relentless pull. One possibility is that the gas is there, just not in the form we expect. Instead of a smooth, glowing river, it might be fractured into clouds too diffuse for our instruments to resolve, like mist scattered by a cosmic wind. Alternatively, fierce galactic winds from nearby starbursts or supermassive black holes could have blown the gas clear of the filaments, leaving behind echo chambers of near-nothingness. But dark matter, immune to such forces, should still linger, unless, of course, it isn't as inert as we've assumed. Here's where the mystery spirals deeper. If dark matter interacts with itself even faintly through some unknown force, collisions within these filaments could have heated and dispersed it over billions of years, thinning it to near invisibility. Imagine two lanes of traffic merging at high speed. The cars might scatter wildly, creating gaps in the flow. Similarly, dark matter particles ricocheting off one another could have spread outward, diluting the filament's density. Supporting this idea are observations of galaxy clusters where dark matter lags behind visible matter during collisions, hinting at previously unseen interactions. Then there's the cosmic timeline to consider. Filaments are ancient, threading the universe since its infancy. Over eons, their gravitational tug should have drawn in more matter, not less. Unless something intervened, perhaps dark energies accelerating expansion stretched them too thin, or early bursts of radiation from the first stars ionized their gas, preventing it from cooling and clumping. The most unsettling theory, these empty filaments aren't empty at all. They could be filled with primordial black holes or exotic particles that don't interact with light, leaving no trace for our telescopes to catch. The implications ripple outward. If filaments are emptier than predicted, the cosmic web might be far more fragile than simulations suggest, its structure prone to voids and asymmetries we don't yet understand. Alternatively, their apparent hollowness could be an illusion, a trick of perspective where our instruments miss the true density hiding in plain sight. Either way, these gaps in the grand design force us to confront a humbling truth. The universe's blueprint is still half erased, its darkest ink fading where we most expect it to be bold. To understand dark matter's origins, we have to rewind the universe nearly 14 billion years, back to a time when the cosmos was less than a second old, a seething furnace of energy so dense and hot that the very laws of physics as we know them may not have applied. This primordial chaos wasn't just the birthplace of atoms, stars, or galaxies. It might also have been the crucible where dark matter first took shape. Unlike ordinary matter forged in the nuclear fires of stars, dark matter's story likely began in those first unimaginable moments after the Big Bang, when the universe was 1 trillion times hotter than the core of the Sun and filled with particles so exotic they've vanished from existence today. One leading theory suggests dark matter could be relics from a phase transition, a cosmic snap, when the infant universe cooled just enough to split fundamental forces apart. Picture boiling water suddenly freezing into ice. The cracks and imperfections in that ice could have trapped remnants of an earlier, hotter reality. These remnants, known as thermal relics, would have been left behind as the universe expanded, too massive and sluggish to keep up with the frenetic pace of ordinary particles. Actions, for example, hypothetical particles billions of times lighter than electrons, might have crystallized out of this transition like dew on a spiderweb, their very existence a whisper from the universe's first trillionth of a second. Then there's the possibility of dark matter emerging from collisions in the quark-gluon plasma, the primordial soup that filled the cosmos before protons and neutrons even existed. In this extreme environment, particles could have fused into stable, invisible form structures so unlike anything in today's universe that our experiments simply can't recreate them. It's as if dark matter is a shadow cast by a flame that's long since gone out, and we're left squinting at the afterimage. The challenge is stark. To test these theories, we'd need conditions far beyond anything modern particle colliders can produce. The Large Hadron Collider smashes protons together at energies that dwarf a nuclear explosion, but compared to the universe's first moments, it's like striking two matches together to simulate a supernova. Even the most ambitious future colliders, like the proposed Future Circular Collider, might only graze the fringes of the energy needed. Without access to that primordial inferno, we're left hunting for indirect clues, anomalies in cosmic radiation, subtle twists in gravitational waves, or the faintest signals from ancient particles decaying in deep space. Yet the most tantalizing hints might come from the cosmic microwave background, the afterglow of the Big Bang itself. Tiny fluctuations in this relic radiation could encode the imprint of dark matter's birth, like fossils pressed into the universe's oldest light. Some researchers even speculate that dark matter's properties might have subtly altered the way galaxies clumped together over billions of years, leaving a signature in the large-scale structure of the cosmos. It's a cosmic detective story where every clue is written in vanishing ink, and the crime scene spans the entire observable universe. The irony is profound. Dark matter, which makes up 85% of the universe's mass, might be fundamentally unreproducible in our labs, a substance whose origins are locked away in a past we can never revisit directly. But that doesn't mean we're powerless. By combining astrophysical observations, particle physics, and computer simulations, we're piecing together a puzzle that predates stars, planets, and even atoms themselves. Each failed experiment narrows the possibilities, and every unexpected observation cracks the door open a little wider. The universe's first moments might be lost to time, but their echoes are still shaping everything we see and everything we can't. Deep in the cosmic archives, astronomers have unearthed galaxies that shouldn't exist, not because they're too big or too strange, but because they're too early. These cosmic pioneers, like GNZ11, shine from a time when the universe was barely 400 million years old, a mere toddler by cosmic standards. Yet there they are, fully formed and blazing with stars, as if they somehow fast-tracked their way to maturity while the rest of the cosmos was still stumbling through infancy. This isn't just a curiosity, it's a direct challenge to our understanding of how dark matter seeds galaxy formation. According to the standard playbook, dark matter halos should have taken their sweet time gathering gas, cooling it, and eventually igniting stars. Simulations suggest the first galaxies needed at least 500 million years to grow from tiny fluctuations into recognizable structures. But GNZ11 and its ilk smash that timeline to pieces. They're not just slightly ahead of schedule, they're rewriting the cosmic clock, appearing brighter and more developed than any model predicts. It's like finding a skyscraper in the middle of a prehistoric jungle, technically possible, but screaming for an explanation. The culprit might lie in dark matter's hidden quirks. If dark matter was warm instead of cold, meaning its particles moved faster in the early universe, it could have clumped together more quickly, creating dense pockets where gas collapsed into stars at breakneck speed. Alternatively, these galaxies might have formed in rare regions where dark matter was unusually concentrated, like cosmic lottery winners born into the densest neighborhoods of the young universe. But even these theories strain to explain the sheer brilliance of galaxies like GNZ11, whose star formation rates rival modern galaxies despite the universe's primordial fuel being far scarcer back then. Then there's the black hole problem. Some of these precocious galaxies harbor supermassive black holes far too massive for their age, as if they skipped the awkward phase of slow growth and shot straight to cosmic heavyweight. If dark matter's gravity truly governed their formation, how did these black holes bulk up so fast? One radical idea suggests that dark matter itself might have directly collapsed into black holes in the universe's first moments, seeding galaxies around them like dark scaffolding. Others propose that the early universe's extreme conditions allowed gas to flow into galaxies with freakish efficiency, turbocharging star formation. The implications are staggering. If galaxies could form this quickly, our entire cosmic timeline might need recalibrating. Dark matter's role as the patient architect of structure crumbles if it could whip up mature galaxies in a fraction of the expected time. Worse, these outliers might not be flukes. Recent observations from the James Webb Space Telescope have uncovered even more too-soon galaxies, stacking the evidence higher that our models are missing something fundamental. Every new discovery peels back another layer of the mystery. Perhaps dark matter isn't the lone puppeteer we thought it was, or maybe the early universe hosted exotic physics we've yet to account for. One thing's certain, the cosmos has handed us a paradox, and solving it won't just explain a few overachieving galaxies. It'll force us to rethink how darkness built the light-filled universe we see today. 66 million years ago, a city-sized comet or asteroid slammed into Earth with the force of 10 billion atomic bombs, unleashing firestorms, tsunamis, and an eternal winter that wiped out 75% of all species, including the mighty dinosaurs. The Chicxulub impactor didn't just end the Cretaceous period, it reshaped life itself. But what if this planet-shattering event wasn't purely random? What if an invisible cosmic force, dark matter, set this catastrophe in motion? At first glance, the idea seems ripped from science fiction. Dark matter, after all, is famously elusive, barely interacting with anything except through gravity. But here's where the plot thickens. Our solar system doesn't just orbit the Milky Way center in a smooth, flat plane. Instead, it bobs up and down through the galaxy's disk like a carousel horse on a merry-go-round, completing a full oscillation roughly every 30 to 40 million years. And when we overlay Earth's geological record, something eerie emerges. Mass extinction events, including the one that killed the dinosaurs, seem to cluster around these cyclical dips into the galactic plane. Coincidence? Maybe not. The controversial theory hinges on a hidden layer of the dark matter halo enveloping our galaxy. Some researchers propose that dense bands of dark matter, like invisible speed bumps, could lurk along the Milky Way's midplane. As the Sun's gravity plunges the solar system through these regions, the extra gravitational tug might destabilize comets in the distant Oort cloud, a vast shell of icy bodies at the solar system's fringe. Imagine flicking a marble into a bowl of pebbles. Even a slight nudge could send debris flying inward. In this case, the pebbles are potential extinction-level comets, and the nudge comes from dark matter's unseen hand. But skeptics are quick to counter. For one, we've never directly detected these hypothetical dark matter substructures, let alone confirmed their density or distribution. And while extinction timelines show rough correlations with galactic oscillations, the matches aren't precise enough to prove causation. The KT extinction that erased the dinosaurs, for instance, occurred slightly after a predicted plane crossing, not during. Then there's the sheer scale of the problem. Even if dark matter did perturb the Oort cloud statistically, most dislodged comets would sail harmlessly into interstellar space rather than target Earth with pinpoint accuracy. Yet the theory refuses to die, partly because it offers an elegant solution to one of paleontology's lingering puzzles. Why do major extinction events appear to have a rhythm, as if ticking to some cosmic metronome? Traditional explanations like volcanic activity or solar flares lack this periodic cadence. Dark matter's gravitational influence, however, could provide the clockwork mechanism behind the chaos. The wildest twist, this idea might be testable. If dark matter truly clusters in the galactic plane, its gravitational lensing effects should subtly distort the light of background stars in predictable ways. Future telescopes like the Vera C. Rubin Observatory could scan for these minuscule deflections, hunting the shadows of hidden mass where our solar system's fate may have been sealed. Until then, the dinosaur extinction remains a tantalizing what if, a reminder that the cosmos's darkest secrets might be written not just in distant galaxies, but in the ancient bones beneath our feet. Hidden in the static of radio telescopes, whispers from the cosmos hint at a universe far stranger than we ever imagined. These aren't signals from distant stars or pulsars, they're the faint fingerprints of entire galaxies made almost entirely of darkness. Astronomers call them dark galaxies, and they might be the purest dark matter realms we've ever discovered. The first clue came from clouds of hydrogen gas drifting through the void, unanchored to any visible galaxy. Hydrogen emits a faint radio signal at 21 centimeters, a wavelength that cuts through cosmic dust like a beacon. When researchers trained instruments like the Arecibo Observatory and the Green Bank Telescope on these patches of sky, they found something bizarre. The gas was rotating too fast to be alone. Its motion betrayed the grip of immense gravitational force, as if it were part of a full-fledged galaxy, except where the stars should have been, there was nothing but blackness. Take the famous example of HVC 214+38, a hydrogen cloud in the Virgo cluster. Its rotation curve screamed galaxy, yet even the deepest optical surveys revealed only a handful of stars, not nearly enough to explain the gas's motion. The verdict: a galaxy where dark matter outweighs visible matter by thousands to one. A ghostly island where stars never got the memo to form. Similar candidates like Dragonfly 44's cousins have surfaced in other surveys, each one a shadowy echo of the galaxies we know. But how does a galaxy end up so starless? One theory points to extreme environments. In galaxy clusters, violent collisions can strip away the gas needed for star birth, leaving behind a dark matter skeleton with only a whiff of hydrogen. Another idea suggests these dark galaxies might be cosmic late bloomers, pockets where gas was too diffuse or too pristine to collapse into stars efficiently. Without the turbulence and metals forged by earlier stellar generations, star formation could have sputtered out before it truly began. The most tantalizing possibility, though, is that dark galaxies aren't failures, they're relics. Simulations show that the earliest galaxies in the universe should have been small, dim, and overwhelmingly dark, their star formation stifled by the harsh ultraviolet light of the first stars. If a handful survived to the present day, untouched by mergers or gas theft, they'd look exactly like the hydrogen ghosts we're detecting. They wouldn't just be curiosities, they'd be time capsules from the universe's adolescence, preserving conditions we've never seen firsthand. Yet for all their mystery, dark galaxies might be hiding in plain sight. Some researchers suspect that what we've found so far is just the tip of the iceberg, that fainter, smaller examples lurk everywhere, camouflaged by the glare of brighter neighbors or dismissed as noise in the data. New radio telescopes like the Square Kilometre Array could soon sweep the skies with unprecedented sensitivity, potentially revealing legions of these shadow realms. The implications are staggering. If dark galaxies are common, they could solve the missing satellites problem by showing that many dark matter clumps never ignited stars at all. They might even rewrite the story of galaxy formation, proving that darkness doesn't always lead to light. Every empty rotation curve, every starless hydrogen whisper, is a reminder that the universe has more than one way to build a galaxy, and we've only just begun to read the blueprint. In the faint glow of the cosmic microwave background, the oldest light in the universe, astronomers found something that shouldn't be there, a pattern so peculiar they nicknamed it the axis of evil. Stretching across the sky like a phantom spine, this axis marks a mysterious alignment of temperature fluctuations in the afterglow of the Big Bang, a signal that defies the core assumption of cosmology, that the universe should look roughly the same in all directions. But what if this cosmic asymmetry isn't just a statistical fluke? What if it's a shadow cast by something far larger and darker, a hidden hand sculpted from the very fabric of dark matter? The anomalies are subtle but undeniable. When researchers mapped the cosmic microwave background's temperature variations, they expected a random, symmetrical distribution like static on an old television screen. Instead, they found a curious preference, fluctuations lining up along a specific plane, as if the universe had a tilted equator. Even stranger, this axis seems eerily aligned with the plane of our solar system, a coincidence so improbable it's been called unsettling by some and impossible by others. Skeptics argued it might be an artifact of instrument noise or foreground interference, but refined observations from the Planck satellite only deepened the mystery. The signal persisted, whispering of a universe subtly lopsided on the grandest scales. Here's where dark matter enters the stage. Simulations suggest the cosmic web, that vast, invisible scaffolding of dark matter, might not be perfectly uniform. Dense filaments and colossal voids could stretch across billions of light years, creating asymmetrical gravitational tides that twist the fabric of spacetime itself. If one of these dark matter superstructures happened to align with the axis of evil, its gravitational pull could have imprinted a directional bias on the early universe, like a fingerprint pressed into wet clay. The cosmic microwave background in this scenario wouldn't just be a snapshot of the Big Bang's aftermath, it'd be a distorted mirror, reflecting the gravitational shadows of dark matter's earliest structures. But the plot thickens. Some theorists propose an even wilder idea, that the axis of evil isn't just shaped by dark matter, but by something beyond our observable universe. Imagine a neighboring bubble of space-time lurking just past the cosmic horizon, its gravity subtly warping our own universe like a magnet tugging at a compass needle. If true, this would mean the axis of evil isn't just a cosmic oddity, it's a window into the multiverse, a glimpse of realms we were never meant to see. Of course, not everyone buys the dark matter connection. Critics point out that the statistical significance of the axis remains debated, and alternative explanations like undiscovered systematic errors or primordial magnetic fields could still account for the anomaly. But the tantalizing possibility lingers that the universe's oldest light carries a message from its darkest component, a whisper of asymmetry written in the language of gravity and shadow. Whether it's a flaw in our models, a sign of unseen structures, or a crack in the cosmic egg, the axis of evil remains one of cosmology's most provocative puzzles, a reminder that even the universe's first light might still be hiding its darkest secrets. We've always assumed dark matter was the universe's most reliable anchor, unchanging, immutable, a silent partner in cosmic evolution. But what if it isn't? What if dark matter evolves, decays, or even transforms over billions of years? This isn't just a wild speculation. Some of cosmology's most stubborn inconsistencies, from the Hubble tension to the perplexing behavior of early galaxies, might find an explanation if dark matter isn't the static entity we've imagined. Take the universe's expansion rate. For years, measurements of the present-day cosmos have clashed with predictions based on the cosmic microwave background. It's as if the universe is expanding faster now than it should be, given the amount of dark matter we think exists. But if dark matter's influence has been waning over time, slowly decaying into radiation or other particles, its gravitational grip would loosen, allowing dark energy to drive expansion more aggressively. Imagine a tug of war where one team's strength gradually fades, tipping the balance in favor of the other side. This could resolve the Hubble tension without rewriting the laws of physics, just by letting dark matter fade into the cosmic background like an aging actor exiting the stage. Then there's the puzzle of early galaxies. The James Webb Space Telescope has revealed galaxies in the infant universe that are too massive, too mature, to fit our standard timeline of cosmic growth. If dark matter was more potent in the past, its stronger gravitational pull could have accelerated galaxy formation, compressing billions of years of evolution into a fraction of the time. Picture a campfire doused with gasoline. Instead of smoldering slowly, it roars to life in an instant. Similarly, early dark matter might have turbocharged structure formation, creating galaxies far sooner than we thought possible. But how could dark matter's properties shift over time? One theory suggests it's not entirely stable. Just as radioactive atoms decay, dark matter particles might break down into lighter particles or even dark radiation, subtly altering their cosmic influence. Another idea proposes that dark matter interacts with dark energy through a hidden feedback loop. As the universe expands, dark energy's dominance grows, but it might also sap dark matter's strength like a slow leak in a tire. The wildest hypothesis, dark matter could be tied to a dynamical field, akin to the Higgs field, whose properties change as the universe cools and expands. Critics argue these theories add unnecessary complexity. If dark matter varies, why haven't we spotted evidence in galaxy rotations or cluster collisions? Yet the clues might be hiding in plain sight. For instance, certain galaxy clusters show dark matter distributions that are smoother than simulations predict, as if its particles have been heated up over time. Others exhibit puzzling gaps between dark matter and visible matter during collisions, suggesting an invisible force is at work, one that wasn't present in the universe's youth. The implications are profound. If dark matter evolves, our entire cosmic history might need rewinding. The early universe could have been a place of exaggerated contrasts, regions where dark matter's pull was so strong it birthed galaxies in a blink, and voids where its absence left vast, empty deserts. Over eons, this imbalance would even out, leaving the relatively uniform cosmos we see today. But the echoes of that turbulent past might still linger, etched in the peculiar arrangement of galaxies or the faint anomalies in the cosmic microwave background. For now, the idea remains on the fringe, a tantalizing what if in the face of unanswered questions. But that's the nature of dark matter. The more we learn, the less it fits the mold we've built for it. Whether static or shifting, this enigmatic substance continues to defy expectations, reminding us that the universe's greatest mysteries are often the ones we think we've already solved. Black holes and dark matter seem like they belong to entirely different cosmic mysteries. One is a voracious sinkhole of gravity, the other an invisible cosmic glue. But what if they're one and the same? The idea that primordial black holes forged in the chaos of the Big Bang's first second could be dark matter has lurked at the fringes of physics for decades. It's an elegant solution. No need for exotic particles when the universe's missing mass is just ancient black holes hiding in plain sight. Yet when LIGO, the Laser Interferometer Gravitational Wave Observatory, began detecting gravitational waves from colliding black holes, this theory didn't just gain traction, it sprouted thorny contradictions. Start with the allure of primordial black holes. Unlike the stellar mass black holes born from dying stars, these would have formed when the newborn universe was a seething, ultra-dense soup. Quantum fluctuations could have collapsed patches of space into tiny black holes, some as light as a mountain, others as massive as a star. If enough of them survived, they'd weave through galaxies today, invisible yet omnipresent, perfectly matching dark matter's gravitational fingerprints. No undetectable particles, no new physics, just cosmic fossils lurking in the void. But LIGO data threw a wrench into this elegant story. When the observatory detected mergers of black holes 30 times the Sun's mass, it raised a glaring question. If primordial black holes are dark matter, why aren't we drowning in them? Simulations suggest these ancient black holes should cluster in halos around galaxies, constantly bumping into each other and merging. Yet LIGO events are rare, implying such heavy black holes are outliers, not the ubiquitous sea required to explain dark matter's dominance. Worse, if primordial black holes were plentiful enough to account for all dark matter, their gravitational lensing effects should have warped the light of distant stars in ways we don't observe. The paradox deepens when you consider size. Tiny primordial black holes, say, the mass of an asteroid, could avoid these pitfalls, but they'd have evaporated by now due to Hawking radiation, a fate predicted by Stephen Hawking himself. On the other hand, heavier ones would have left glaring imprints on the cosmic microwave background or gobbled up neutron stars, leaving traces we've never found. It's as if the universe is teasing us with a Goldilocks zone for primordial black holes. Not too big, not too small, and frustratingly elusive, yet the theory isn't dead. Some researchers propose a compromise. Maybe primordial black holes make up only part of dark matter, with the rest being something else entirely. Others speculate that LIGO black holes are primordial, but represent a rare subset that survived in dense pockets, leaving the majority still undetected. There's even a wild card. What if primordial black holes aren't entirely dark? Theories like quantum hair suggest they could emit faint radiation or even harbor exotic particles in their orbits, creating observable signatures we've yet to recognize. The stakes are cosmic. If primordial black holes are dark matter, it would mean the universe's greatest mystery was under our noses all along, hidden in gravity's darkest corners. But if they're not, their eerie absence forces us to confront an even deeper enigma. Why does the universe refuse to give up its secret so easily? For now, the paradox stands, a gravitational tug-of-war between elegance and evidence, where every new detection could either solve the puzzle or deepen the darkness. What if dark matter isn't just hidden? What if it's from an entirely different universe? This isn't science fiction. Some physicists speculate that dark matter could be the ghostly imprint of a mirror cosmos, a parallel reality where particles echo our own but barely interact with them. Imagine a world identical to ours in structure, yet invisible, its atoms and galaxies made of shadowy counterparts that pass through us like phantoms. This mirror universe theory isn't just a wild thought experiment, it's a serious attempt to explain why dark matter feels so close yet remains so maddeningly out of reach. The idea hinges on symmetry, a principle baked deep into physics. Just as matter has antimatter, some theories suggest our universe might have a twin, a realm where the rules mirror ours but with subtle, eerie differences. In this shadow cosmos, protons, electrons, and stars could exist but built from particles that scarcely notice ours, interacting only through gravity. That would make dark matter not an exotic particle in our universe, but ordinary matter from another. Every galaxy in our night sky would have a dark counterpart, every star a silent double, forever unseen but gravitationally tethered to us. Evidence for this mirror world is thin but tantalizing. Certain neutron stars, for example, seem to cool faster than physics predicts, as if their heat is leaking into another dimension. Then there's the puzzle of why dark matter halos around galaxies are smoother than simulations suggest. Perhaps because mirror universe particles interact weakly with each other, spreading out more evenly than expected. Even the cosmic microwave background's odd asymmetries, like the infamous axis of evil, could hint at gravitational whispers from this other realm. Critics argue the theory is unfalsifiable. How do you test a universe you can't touch or see? But scientists have proposed ingenious experiments. If mirror particles occasionally bump into ours, sensitive detectors might catch the faint recoil, like hearing an echo in a silent room. Others suggest looking for distortions in gravitational waves, which could carry imprints of hidden masses from the mirror side, the wildest possibility. A mirror universe might have its own dark matter too, creating an infinite regress of unseen worlds stacked like cosmic nesting dolls. The implications are dizzying. If true, the mirror universe would mean dark matter is just the tip of an iceberg, an entire shadow cosmos humming alongside ours, its history and fate forever entwined with ours but forever separate. It's a humbling thought. The 85% of the universe we call dark might not be missing at all. It might simply be living next door. The cosmic dark matter web has been the unseen architect of our universe for billions of years, sculpting galaxies and guiding their dance across the cosmos. But what happens when the music stops, as the universe ages, stretching toward a future so distant that stars themselves flicker out? Dark matter's role could transform in ways that rewrite the fate of everything. Picture this: trillions of years from now, long after the last stars have burned to ash and galaxies have evaporated into the void, dark matter remains. Unlike ordinary matter, it doesn't decay or radiate. It simply persists, a ghostly skeleton in an ever-expanding graveyard. But even ghosts might not last forever. Some theories suggest dark matter could slowly evaporate, its particles decaying into faint whispers of radiation over timescales that make the age of the universe seem like a blink. If true, the cosmic web, that vast, invisible scaffold, would fray like an ancient tapestry, its threads dissolving until gravity's grip weakens completely. Galaxies already drifting apart would accelerate into the abyss, their last gravitational ties severed. Yet there's another, stranger possibility. What if dark matter doesn't fade but clumps? In a cold, dark universe, free from the disruptive turbulence of stars and supernova, dark matter halos might collapse into dense knots, drawing together like shadowy continents on an invisible map. These aggregations could birth structures unlike anything we've seen: black holes made purely of dark matter, or vast, dark galaxies where phantom mass outweighs anything left of the visible universe. Simulations hint that such dark matter, black holes, could grow to staggering sizes, their gravitational wells warping the fabric of space-time long after light itself has dimmed. Then there's the wild card, dark energy. As the universe expands, dark energy's repulsive force grows stronger, threatening to tear apart not just galaxies but space-time itself. But dark matter's gravitational pull might resist this fate, creating pockets where the cosmic web holds firm, even as the void between filaments stretches to infinity. In these oasis-like regions, dark matter could become the last glue binding remnants of the universe together, a final bulwark against total dissolution. The most unsettling scenario, dark matter and dark energy might not be independent players but locked in a slow cosmic duel. If dark energy's acceleration triggers phase transitions in dark matter, altering its properties or interactions, the universe's fate could hinge on a hidden battle we're only beginning to fathom. Imagine dark matter crystallizing into a new state or fragmenting into exotic particles that accelerate expansion even further. The end result could be a cosmos so alien our current physics can't even describe it. For now, these are speculations scribbled at the edge of cosmology's map, but they remind us that dark matter isn't just a static backdrop. It's an active participant in the universe's story with its own destiny still unwritten. Whether it fades, clumps, or transforms into something beyond our imagination, one thing's certain: the dark web's final act will be the ultimate plot twist in the saga of existence. And by then, there may be no one left to read the last page. From the ghostly rotation of galaxies to the whispers of dark matter decay, these 25 mysteries aren't just gaps in our knowledge, they're the edges of discovery, the places where science bends and stretches toward something new. Think about it, every time we hit a wall, like the missing satellites problem or the Hubble tension, we don't just stop, we rethink, we rebuild. The bullet cluster didn't just confirm dark matter's existence, it forced us to ask if dark matter interacts with itself. Those early, too bright galaxies spotted by the James Webb Telescope didn't just break our models, they made us wonder if dark matter was different in the universe's youth. Even the eerie alignment of the axis of evil challenges us to question whether the cosmos is truly uniform or if dark matter's hand tilted the scales. Then there are the wild cards, the primordial black holes that might be dark matter, the mirror universes lurking just beyond our perception, the possibility that dark matter and dark energy are locked in a cosmic tug-of-war. These aren't just ideas, they're invitations to explore, because here's the beautiful truth: every mystery we've uncovered isn't a dead end. It's a detour into something stranger, a signpost pointing toward physics we haven't even imagined yet. So let's turn the spotlight to you. Which of these mysteries keeps you up at night? Is it the dark flow dragging galaxies toward some unseen horizon? The ghostly galaxies with no stars, or the ones that formed too early? Maybe it's the decaying dark matter theory, or the chilling thought that our universe's fate hinges on an invisible substance we still can't touch or see. Drop your thoughts in the comments. Let's geek out over the cosmos' biggest puzzles together, because the best part of science isn't having all the answers. It's the thrill of the hunt, the collective gasp when someone says, "Wait, that shouldn't be possible," and right now the universe is full of those moments. So stay curious, stay questioning, and who knows, the next big breakthrough might start